Hello everyone, August the 4th. The recovery is happening. I feel getting slightly better, but overall still not too good. I tried to eat something more solid today. It was okay. I mean, it's okay, but I don't think I'm ready yet. That's basically the point. And also, I'm deciding not to train today, but I will train tomorrow. I think tomorrow shall be ready to train and also eat something more solid in the morning as well. And what else? I weighed myself today, and as I expect, once I stop training, I just lose weight a lot. I think last week was 158, 157. Right before the surgery, and today is 154. And I feel weak, very weak. I feel like it's gonna take take a few sessions to get back into shape. And in fact, I think my wrist probably is not even in shape to do snatch now. That's the thing. Like if I stop snatching, I can't get back snatching really fast because the wrists just don't handle the weight as well. So tomorrow will be 5 days. 5 days without snatching. Today is 4. Today will be 4 days. No, 5 days. 5 because last Thursday I did not snatch. So today is 5 days without snatching. Yeah, I think the wrist, if I try it tomorrow, the wrist will definitely feel it. Hello. Alright, let's get on to it. It's an easy problem today, so that's good news. Fruits into baskets. We had fruit into basket yesterday, and that one was a medium question, and this one is an easy question. Interesting. So I have two arrays of integers. Fruits and baskets, each of length n, where fruits I represent a quantity of the ith type of fruit and basket. J represents the capacity of the jth basket. From left to right, place the fruits according to these rules. Each fruit type must be placed in the leftmost available basket with the capacity greater than or equal to the quantity of that fruit type. Each basket can hold only one type of fruit. If a fruit type cannot be placed in any basket, it remains unplaced. Return the number of fruit types that remain unplaced after all possible allocations are made. So essentially we're saying the fruit type must be placed in the leftmost available basket with a capacity greater than. So you cannot change the order of the basket, right? So for this, I need to put the leftmost available, which is this one, so I can put it in. For this, the leftmost is 3. For this, we only have 4 left, but you cannot place it because the capacity is 4. So you have 1 unplaced. Okay, so what I need to know is how do I easily find, you can do O(n) squared, right? But there got to be a way to find the leftmost. I think a stack? Would a stack work? A leftmost, a stack? I don't think so. Like, how do you know if anything else? Huh, I don't know. I have no idea. What would be a faster way to do this? A leftmost that's bigger. How do you find the leftmost that's bigger? Can we sort fruit? Well, if we sort fruit, then we're saying we're matching the smallest. But that's not right. Right? That's not right because the basket is not. We cannot sort the basket. I mean, if you have to go fruit also left to right, then there's basically no way else to do this. You have to go the fruit left to right as well. It's just if the current fruit can match the leftmost basket, then we can move everybody down, right? That's good. Now if the current fruit cannot fit the current basket, that simply means the current basket is too small. So now we move the basket down. Okay, then we'll keep moving until we find one that fits. But then that's still O(n) squared. Dude, is there a not O(n) squared? Oh, I guess this is O(n) squared then. Huh. Yeah, I mean, if we cannot move if we cannot change the order, then yeah, I think it is O(n) squared. Well, since we cannot change the basket's order nor the fruit order, O(n) squared is the only option. Ugh. Yeah, we can go with fruits. If basket I is larger or equal to f. Oh, would it be 0? No, it would not be 0. Then rest of plus. Oh, shoot. Okay, so we actually do unplaced, placed. No. that should do, right? Okay, we might want to go through this one. Oh. Oh, this one. I remember someone has this. Huh. I don't remember this one at all. Oh, holy crap. I was wrong? Oh, yeah, I forgot to break. Sorry. Wait, hold on, there is a faster solution. Oh, wait, no. But why somebody has such a high 0? What did they do? That was exactly the same. Maybe have more test cases. Alright, that's it. Okay, I don't think I have the gana to really redo this one. Let me just go back and then check it one more time. What was the question again? After removing one conflicting pair. So I've got conflicting pair. We're finding the total smallest, because this is the... Oh, actually, no, this is a different problem. This is to get the smallest, right? Beaming, I think, yeah, we have a smallest and the second smallest. Because what we identify is if we remove it in pair, if the removing pair does not contain the smallest, then we don't have, there's no change in the result. But if the removal is the smallest pair, then we need to adding back the amount of deleted by using the second smallest. So yeah, so we get the smallest, second smallest, and then we have the number of deletion, and then we go from right to the left for every single one, starting from this, right? Basically starting from this, we're trying to see how much we can get, right? How many subarrays that is included, right? How many subarrays can be included? And then we're also updating the minimum, right? This is the index of the minimum. And if this is larger, this one is actually smaller. It's like overall we have a smaller than B2. B2 will pointing to the second smallest, which is B2 or this, right? That's the second smallest, and the smallest pointing to here. If not, then B2 will get updated by this. Yes, B2 always point to the second smallest, and then IB1 is pointing to the smallest one. And this is the number, the total number that we can add, that includes, right, the number of subarrays that can be included. It depends on the minimum and, right? Depends on the minimum and. Wait, what was the question again? I need to remember. Which do not contain AB for any remaining conflicting pair. Oh, do not contain both. Okay, yeah, do not contain both. So we don't want to contain both. So from every starting point, you want to find the smallest. Yes, you find the smallest. So this is the number of subarray that you can get that do not contain both, right? And you also want to know what's the number of if the current gets deleted, right? The current, if the minimum gets deleted, what additional can be added back? So that will be, you have this minimum is this, right? Basically, if it's not the scenario, right, then this will be the smallest. Hold on, let me think again. Now I think it's if the current position can be deleted. Yeah, it is the IB1 if the minimum gets deleted. If the minimum gets deleted, then how much more we can get for, like, starting from this position, right? How much more we can get starting from at I, how much more we can get? Well, that depends on what's the second smallest, right? And the second smallest minus the smallest, that's the difference. That's the amount you can get. So yeah, we do that. Keep doing that, and eventually you will. We might swap the IB1, so you get the del count at a different position, and at the end we pick the largest of them, right? Which means because you should definitely remove the smallest, but you don't know which smallest to remove. But now what we record is for each smallest to remove, what is impact, right? What's the impact, and then you pick the largest of those impact. Yeah. Did I upload this? Yeah, this is actually really good. Alright, I'm gonna close this. That's it.